Okay, folks, good afternoon. This is 4 o'clock, so we're going to start our presentation for Lab 53. Just to let you know, a few of your friends, classmates emailed me, and somebody today too, saying that thickness, wall thickness that I gave 0.01 and 0.02 are so small compared to the load that is applied that gives a deflection of, I don't know, half a mile or something like that. If you have already submitted your homework, don't worry about it. But if not, then you want to use more meaningful numbers instead of 0.01, which is one. I think 0.01 is almost a tenth of a millimeter thickness. I'll make it 0.1 and 0.2 inches. Okay, yeah, and then do it and submit it. I mentioned that the GAs, unless there is a gross mistake, they don't take off marks for things like this. Basically, it's let's blame it on me. I give you a number that doesn't make sense, but at least some of you got it, saying that, hey, colors look good, but numbers don't make sense. Half a mile deflection of something. Okay, good. So if there are no questions, I will move on with my presentation. Any urgent questions?
Hello?
Yes, yes.
Yeah, Dr. Zamani, can we like cut it in the XY plane?
Are you talking about the homework for today? Is that what you're saying? Is that the one that you're talking about today?
Yeah, the assignment.
Okay, so we do that after my presentation, okay? After my presentation, I'll bring up the assignment because I don't remember what it is, and then we can look at it, okay?
Okay, no problem.
All right. So today is the last presentation on shells by themselves. I told you that shells and beams are going to come back again, but perhaps maybe a week or 10 days down the road, where we have problems that you need to have in it: solid element, beam element, and shell element. Okay. At this point, we only have one kind. Now, yeah, so let's look at this problem, which is from chapter 12. So we have a thin-walled pressure vessel, and it's internally pressurized. And remember, from your Deformable Bodies 1, you actually came up with some working formulas for something like that. As a matter of fact, as a mechanical engineer, there are several things that you should never forget. Several formulas that you should never forget. And I'm talking about the strength of material side or solid side. One of them is F equal to MA. Everybody knows that. F equal to MA, obviously. Then it's sigma equal to MC over I. Bending stress in a beam. Then it is PR over T, the hoop stress in a thin-walled pressure vessel. These three formulas are extremely important, and they're handy. They come to your assistance quite a bit. Now, here we are. This expression was given to you. And by the way, look, if the internal, for example, in this particular problem, we have a pressure of 100 psi, and the wall thickness of 1/10 of an inch, and radius, nominal radius of 6 inches. One thing about this wording, nominal dimension. Now, I'm going to say that because if you see it on a test, that should not shock you. Nominal dimension means that, okay, one thing you know for sure, this problem has to be done with shell elements, okay? And if you're gonna model this thing with shell elements, you need a surface. The radius of that surface, this cylinder, is 6. That is what is called nominal dimension. The actual pressure vessel goes 0.05 inch outward, 0.05 inch inward. That is why we call this thing nominal dimension, okay? Now, obviously, if you were doing this thing with solids, and you should not, if you're doing it with a solid, Nominal dimension, of course, kind of doesn't, it means the middle of that solid that you were trying to generate. Okay, so we know what nominal is. After any issues, let me know. We're gonna clarify it further. Okay, now notice that the internal pressure is 100 psi, but when you look at PR over T, R over T is 60. So the hoop stress in this innocent cylindrical pressure vessel is 6,000 psi. The internal pressure is 100 psi. That's the force that it exerts, or force intensity that it exerts on the wall, but that causes a hoop stress of 60 times bigger. The multiply by R over T. R over T here is 60. Okay, and of course axial. If the ends are capped, you are also shown in your deformable bodies too that the axial stress in this cylinder is half of that, 3,000 psi. Now, the stress through the thickness, we assume it is zero. It is not zero, because right at the inside of the vessel, you have 100 psi. On the outside of the vessel, you have zero. So that pressure, that stress through the thickness is not zero, but it goes from 100 to zero. Inside 100, outside zero. And look what we're comparing it with. We're comparing with 6,000 psi and 3,000 psi. So we assume that the stress through the thickness is zero, and therefore we can use shell elements. Just a comment, in a stress analysis course, not the one that you took though, the advanced version of it, or intermediate version of it, you also discuss thick-walled cylinders. Thick-walled cylinders, the stress, that thickness is not so small that we can ignore saying that, oh, it goes from I don't know, from 100 to zero. Okay, if that is thick, that pressure may not be, that pressure may be significant, and you have to consider that. Okay, for example, if you look at the barrel of a cannon, it's pressurized, but it's not thin. And there, that radial stress, that through the thickness is important. And although it may not be quite as high as hoop, but it is significant that it will basically contribute to your von Mises stress and yielding and things like that. Okay, let's stop for that. We are taking these for granted. Now, well, first of all, notice that due to symmetry, I can make a cut halfway through this. Halfway through this, I can make a cut. There is no reason for me to do the top and the bottom. Absolutely no reason. And then I can also take a slice. If this hypothetically was a, I don't know, 30-degree slice. It says 45, I understand that. But I'm saying, suppose it was a 30-degree slice. The next slice next to it, 30 degrees. The next slice next to it, 30 degrees. All the way around. There's 12 of them, right? If it's 36 degrees. If it's 30 degrees, there is 12 of them. They're all going to look the same as far as the stress distribution is concerned, as far as bulging is concerned, etc. So if that is the case, why should I bother taking, I don't know, the whole thing? Okay, I'll cut it. I understand that. I cut it halfway in the middle. But also, I need to take a slice only. And then, of course, you have to put symmetry restraints on these free edges that you create. Here is the thing that I've taken. In this particular problem, I've taken 45 degrees. Really doesn't matter. And so basically, this is the thing that you're going to model. This is the thing that you're going to create geometrically, and then mesh it with shell elements, and then proceed. However, on purpose, I will throw a curveball at you. If this angle instead of 45, it was 90, then when I take one edge, these two side edges lies, for example, hypothetically in the YZ plane. If I take the other two edges, if it's 90 degrees, they will lie in the XZ plane. So I can use the good old user-defined restraint and say translation in 1 and 2 and 3, etc. You know the rule. But if this is 45 degrees or 30, anything but 90 pretty much, then one of them can be thought of as being in the XZ plane or YZ plane. The other one is going to be off that plane. Now, when we did rotating disk problem a couple of weeks ago, we didn't have that issue because there I told you that in the book I throw a curveball at you, but here I'm going to say don't worry about it. Use surface slider. Surface slider doesn't care what the orientation of this is. There's a surface here, but you cannot use surface slider in shells because these are these edges. These are not, these symmetries are edges. They're not surfaces. So this is on purpose, because this issue of local coordinate system or axis system is extremely important, and this is the right time for you to see it. I bypassed it when I did the rotating disk problem, but now I'm going to do that. Okay, let me see now. Are there any questions? Okay, no questions. All right, let's go ahead and do this. And I want to remind you, when it comes to these problems, there's different ways of doing it. One is you can create the surface by extracting a solid. And then, of course, and then you may have to join it. The other one is direct generation. So we have enough time to do for my 50 minutes. So I'm going to do both ways. My first approach is direct generation, not using the surface, not using the extracting of the surface. So let's start with the part file. Here's the part. Say OK. Say OK. Immediately save. File, save management, save as. Okay, desktop. Where's my desktop? Desktop, a new folder. I'll call it Lab 53. 53. And today is May 31. Unbelievable. Okay. So everything is going to go in here. And the first approach is your student ID number 123456789 dash. Your ID number. Ooh, how about calling you Rankin? This is not Dr. Rankin, it's the Rankin, the British physicist. Okay, and then we have surface generation. How about that? Yeah, okay, let's give it a meaningful name. Lab 53. Direct surface generation. Direct surface generation. Okay, let's do it. I want to remind you that on the test, you're going to have imperial units only, inches, pounds, blah, blah, blah. Okay, and we'll talk about that later more slowly. All right, so I want to create this surface directly. Where is that? Yeah, this surface directly, and my approach is draw this L and then revolve it. Okay. Okay. So on this plane, I will sketch my L, which is half the height of that original vessel. Okay, let's dimension it. So this is 20. Okay, and this guy is 6, radius 6. 6. Very good. And I want to revolve this so that it gives me that guy. What do you suggest I do? First of all, I exit this. Okay, I exit that. I understand. Now what? Can you help me?
You can shaft it.
Good, except that shaft will not give you a surface. This is for part design. As a matter of fact, let's try it. Let's try it. What happened? You're going to get something that is not really. I mean, what is this? I don't know. Let's try Z-axis. See what happens. It goes nuts. Basically. All right. So cancel that. Any other suggestions?
You can do it around the y-axis, and then it would create that surface.
Okay, here's what I'm going to suggest to you. The approach that you're giving me, I don't know. It may work, it may not. I don't know. I suggest that people try it. But if you're creating surfaces, don't be here. Go to generative shape design. That's what I wanted to for somebody to tell me. Okay, now there is something called revolve right there. Actually, this is solid volume. There must be revolve somewhere here. Where is this extrude? This is the extrude. Oh yeah, right there. You see that? Revolve. Revolve is for creating surfaces. Okay. Shaft, in part design, is primarily for creating a solid object. Now you may want to try shaft. It's not going to give you a surface, I guarantee you that. But try it. Try it. Okay. We are going to use revolve. And we're going to go 45 degrees, right? We said 45. Let's try 45. And the sketches, of course. Oh, we have to say about what? About the z-axis. And there we are. Okay, without giving me a surface, without giving me a solid object, it gives me, give me my surface. Now notice that those rear edges, the one that I drew my L, lies in the YZ plane. No problem. But these front ones, they do not lie in any of these important planes that I can use the, is it the other way around actually? Oh yeah, see the front one lies in the YZ plane. The rear one do not lie in any of these conventional XZ, XY plane. Okay, good. So I don't need to join this. If in doubt, join it, okay? I don't need to join it for the same reason that when I extruded something, I did not have to join, okay? In the second approach, where I create a solid object here, and that's where, of course, by the way, I'm going to shaft and then extract the faces, I will have to join these because these guys will not be talking to each other. Not here, though. This is fine. Okay, so let's go ahead and apply material to this thing. I don't know what I said. Let's use steel, okay? I like steel. There we are. Okay, very good. And we save it. Now, let me hide, by the way, this sketch, the original sketch. Let me hide it. Or I'll do it over here. Hide. Once again, I want to remind you, that sketch that I just hid was in the YZ plane. So when it comes to symmetry, I have no problem. I say no displacement in global X because he was in the YZ direction, no displacement in X. And of course, same thing with rotation, same type of thing for rotation. But these two other edges, because I took 45 degrees, will not lie in the YZ plane or XZ plane, etc. If I had taken 90, by the way, it would have been in the XZ plane. But I said, I'm going to make your life harder. Okay? I didn't. So here's what I'm going to do. I'm going to create a coordinate system, axis system, okay? So let's find it. First of all, for an axis system, you can't miss it. It just looks like an axis. The only thing is I may have inadvertently closed this thing, and I honestly don't know what the name of that toolbar is. If somebody sees it, let me know. Or if you don't know it, let's go ahead and reset our toolbar. So let's go ahead and do that. Tools, customize. Wait for a second. I don't like it when it says not responding. I don't know, but that's okay. It'll come back. Okay. So here we are. Toolbars. Restore all contents. restore all positions. Do not forget this, because at some point you may forget what you closed and you need it. So it's right here. See that? This guy right there, access system. It's called tools. Okay, let me close that. Now I click on it. As soon as you click on it, it immediately creates an access system for you at the global origin, and the axes are aligned with the global coordinate system. I don't want that. I already have it. I know that. I want this thing to be aligned with these lines. So first of all, to make us see it easier, let me change the origin from here to here. So for origin, see that? It says origin. I'm going to select this one. It puts it up there. It's still not aligned with the thing that I want. It's aligned with the global one. So I have the opportunity to say, where does X go? For example, look, for example, I say X. I'm going to say, oh, I want my X to be along that edge. It will turn that thing, and notice that it puts the X along that edge. And of course, Z is going to be perpendicular to, etc. This coordinates, if I use this coordinate system, because these two edges lie in the XY plane of that coordinate system. If I had done it differently, it would have been different. But the way I did it, these two edges, back edges, lie in the XY plane. No displacement in Z, rotations opposite of that coordinate system. Okay? So let's go ahead. We created that because we're going to need it in a few minutes. Okay. Now we're going to go to generative structure analysis. No fancy measures for us. When they pay you, you're going to have to do that. Okay. There is my horrible triangular mesh. You select this. Notice that the whole thing is picked. If these were in a sense not joined, when I would pick this, only the bottom piece will be meshed, etc. That's going to happen in the second round that I do. Okay, so there we are. Okay, so let's make it 1. I'll make it linear. I'll look at the mesh. There we are. And because of the fact that this is kind of joined already, because of what I did, I revolved it. Notice that when I select this element, it goes, that edge, that seam is between 28, 29. And when you go on this side, it's still 28 and 29. If these were extracted and not joined, these will be different node numbers. This goes nuts. Okay, I mean, it'll bomb out basically, unless you use connections to, you know, to tie them together, which I said we're not going to do that for shells right now. Okay, deactivate this, deactivate that. Okay, very good. Now thickness right there, 2D property. Because the thickness is the same, all I need is to pick it, I put the right thickness, and I think 0.1, right? 0.1 inch. That's what I said. Can you tell me what happens if these thicknesses were different? What would you do?
Doctor?
Yes? Yes?
Would you have to create the two surfaces independently and then mesh them independently?
Yes, that's one way of doing it. But I showed you a different way. Without, because if you go that route, then you also have to tie them using the connection property, fasten, etc. But I show you a different way of doing it.
Local 2D property, I think.
Local 2D property, yes. Local 2D property. You see, you specified right now 0.1 on the whole thing, but you can go there, you say local 2D property, and then you go select this guy and say, oh, it does not 0.2, or it's not 0.1, it's 0.05, etc. That is a lot, I don't know, more straightforward, not a lot, more straightforward than that process of fastening it as that you are suggesting. Do them separately, etc. Not that that is not important, it's just that this is more straightforward. Okay, now we're not going to do that because it's the same thickness, by the way. Okay, then Then we're going to apply pressure right here, pressure, and just be careful. You want to select this. It puts it on that surface. Okay. By the way, it's wrong. This is going to suck it in. Okay. And this one, let's try that one. Both of these, we put a minus sign. Notice that I selected them simultaneously, but I need a minus sign if this is internally pressurized. Okay. All right. Very good. Let's save our analysis before anything goes nuts. So file, save management. There's the analysis. Save as. I'll move this thing so that I can see the name that I used here. I know I called it Rankin, but okay. So okay. Okay. Let's see now. 1, 2, 3, 4, 5, 6, 7, 8, 9 dash Rankin. I think the rest of it I call direct generation or lab 53. Lab 53. A direct generation. Direct surface generation. I think, what did I call that thing? Part. Okay, this is going to analysis one. That's good. Okay. Now, so let's worry about our restraints now. Okay, user-defined restraint. Uncheck all of these. It's a good idea to uncheck these things. Okay. So this bottom edge. See that bottom edge? See this bottom edge? Is that in a plane of symmetry? I'm pretty sure you agree because I cut it to the XY plane. And the XY plane, you have to be careful here because there's two XY planes. One of them is the global one. See, it's a global right there. But there's also the local one. As far as this guy goes, it is in the global XY. You see, global right there. Global XY means does not move in Z. Translation in Z is fixed. And rotations are opposite. Don't forget the rotations. You have to do it. No part marks. Okay. Let's look at these two front edges. Once again, you know what? I suggested you to call these things with names that you recognize. On purpose, I say XY global. How about that? Global. Just so that you can see what you have done later on, if needed. Now, these two edges, the other two edges, let me uncheck all of these. It's this one and that one. And I can call it, that'll be YZ global, right? YZ global. YZ global. Okay. YZ means does not move in X. There. Does not move in X. And rotations are opposite. And say okay. Now we come to those back edges. So, once again, uncheck all of these. But global one is not going to do me any good. I have to go and say user. It says, okay, which one? Well, I have only one, so I pick this. So whatever you see now is going to be with respect to this coordinate system. First of all, I will put here, it lies in the XY user. XY user. These two edges that I picked lie in the XY plane of the user coordinate system. And immediately it says no Z, no translation in Z, and rotations are opposite. Okay. Any questions? Any comments? Oh, I forgot to select the support. Here, the support of these two back edges. This guy and that guy. Yeah. I forgot to pick it. Now I did. Now I can close this. And save it. Save it. always pray. Maybe it'll be good to you. Okay, what this is saying is not a good mesh. You know, basically I have a horrible mesh. That's what it's saying. It's going to show you stuff. I can make it smaller, or I can make it perhaps parabolic. Let's try. This doesn't say it didn't run. It just cautioned you that, hey, you may be getting stuff that is, let's try parabolic, see whether, this is a simple enough problem that it's going to run very quickly. We'll see. You see? It said with the first one, that mesh, do it, but you're on your own. Or we don't guarantee anything. They don't guarantee anything anyway. So, okay, so let's look at the deformation. All right, so deformation. No numbers. Animated. Well, that's the way it should be. And remember that this end is very flimsy. There is going to be a deflection. It's going to be a lot bigger than this guy becoming fatter and longer. Now, this is for exaggeration, of course. If you want to see the actual deflection in terms of the dimensions that we have here, you set the scale to 1, not 3. It's going to be a little bit better. That's a little bit better. Still, the end bulges out. You know that. Because it's very stiff to expand in the hoop direction, but it's not very stiff in this direction. Now let me put the scale back. Okay, now you want to see numbers? Okay, so let me double click, change the rendering. It says that this tip, the tip is basically the center of that circle at the end, deflects by almost 1 inch. That's a lot. Considering the fact that dimension of this radius was 6, to say that this deflects by 1, in all likelihood, it's going to go into, it's going to yield basically. Well, I don't have a magic ball to predict that, but let's plot the von Mises stress. Yeah, 200,000. Yield strength of the steel is 30,000. This is 10 times bigger. We know that. Okay. Now, a few things. First of all, this is all garbage. This red stuff is all garbage. And this is all garbage. Because if you really want to know what happens to a tank like that, at that juncture, a lot of nasty things will happen. That stress through the thickness being 0 is not applicable here. So if you really want to know what's going on here, you probably need solid elements here, solid elements, not shells, and then over here, and here, shell elements. Okay. Now, but there is one thing I can confirm. Let me plot the principal stresses for you. The principal stresses, contrary to the one that was totally useless in beams, because it only gave you the axial one, this will actually give you the principal stresses, the stuff that you did in your deformable bodies class and your stress analysis class. And if you stay away from that bad zone, this is a bad zone. If you stay away from it, you go to the middle of the tank, down here, this is the middle of the tank, and you put the cursor on it, look at what it says. Okay, let me look at the numbers. This is the hoop stress, better be 6,000. 6,020. Look, it says right there, 620. This is the axial one, it better be 3,000. Look, down below, 2,930. These formulas that you will never forget as a mechanical engineer, PR over T, MC over I, let's stick to PR over T, are valid for an infinitely long cylinder. Or look at it this way, extremely thin cylinder. Because it's extremely thin cylinder, it becomes infinitely long as far as the thickness goes. So those are good formulas, and we just confirmed it. And but it's totally garbage when you go to these areas. And perhaps as a designer of this tank, you, somebody who designed it, you're going to sign under that document, you have to worry about this. Okay? Yeah. Okay, any questions? We have another 15 minutes to go through the same process, except that I'm going to do it let's think about it. Think about it as the book way. It's not the book way. Any question? Any questions on this issue? Okay, on this problem.
Doctor?
Yes.
I just have a question about kind of why we would do this. You said that it's not completely wrong, but why would we use shell elements if it's not completely right?
Okay. Okay. Let me give you an idea. Suppose there was an opening here, which was attachment to some other gadget, a pipe or whatever. This PR over T and PR over 2T is totally useless. Those are useless because the PR over T assumes that you have a uniform wall, you have a uniform geometry. But if there was a, it was a hole here because you had to pump in, I don't know, pump in air or whatever in there, then forget about PR over T. Then you have to do a good mesh in problems, in places which are problematic. You cannot use only shell element. Rest of the structure you can do shell. Close to those opening, close to these seams, you have to do solid element. And this is something that it will take time. You cannot sit and do it, in 15 minutes that I'm doing. It takes time. It takes time. This is valid. This PR over T is valid for just the cylinder. Forget about the ends. Very long cylinder. Okay. But if you have holes, all bets are off. There are no formulas like that anymore. Yeah. Are we good? Or at least I try to give you a reasonable answer. Let me also give you another example. If you have the wing of an aircraft, let's say it's made of aluminum, very thin aluminum, and the skin is a shell. It's a shell. So the aerodynamic load that comes from your, your courses on aerodynamics, that pressure is you're going to apply, and then you look at the stress distribution in the shell. Okay, at the places where these things are attached to some other stuff, stringers, blah blah blah, or ribs, then you have to be very careful, very careful. Okay. All right. I think that kind of at least tries to try to explain. Okay, so let me kill this. Let me kill this. Save it and kill it. I'm going to repeat the same problem, except that we're going to do that using first creating a solid object and then extracting. We don't care how you do it. This is why I still have time. I want to show people if they want to go that route, by all means. Okay, so what are we doing here? Okay, let's start with the part file. Immediately save it, file, save management, in that folder, except that I'm going to call it surface extraction. How about that? Surface. Sounds very mouthful, surface extraction. All that means is make a solid object and then get the surfaces. Okay, so I'm gonna on that plane, just like before, I'm gonna draw my inverted L. I can't get over that question that you asked. Why are we doing it? Let me try to put it a different way. You want to eat your steak, okay? If you want, you can eat it with a razor. You can get a razor and cut it instead of a knife, cut it into pieces. You can do that. And for certain size steaks, it may be okay, but there may be situations where that's totally useless. Okay, I think that's a better explanation, I hope. Okay, let's make this thing 20. Excellent. Exit. Now we want to shaft it. Remember, we are in generative shape design. If you want to shaft it, means that you're trying to get a solid object. You can't do it here. That's not quite true these days, but I'd rather take you part design because it's possible to generate solid object in generative shape design, but don't do it unless you know what you're doing. Okay, so shaft is right here. Okay, so it's this. I don't like it when something is pre-selected. Let's try it. Okay, try it again. This. Okay, about the z-axis. Oh, it has to be closed. I see. I'm sorry. Let's do that. Let's do it. Let's go back here. Oh no, shaft says that you have to have a closed curve. You can get it to do it for you, but there we go. That's better. Okay, exit. Come on, exit. Are we there? Oh, there. Exit, and now we can shaft it. Shaft that sketch. About, for example, that line or Z, but we want to go only 45 degrees, I think. 45. Very good. Okay. Let me create that coordinate system that I did before. I can do it here while I'm in part design. That's okay. We also have that guy somewhere here. Right there. See that? Axis system, just like before. I'll put the origin here. And I said that I'm going to line up X with that. We don't have to. We can do it differently, but that's what I'm going to do because that's how I did before. And by the way, now that I did it, it looks different because the other time X went this way. I don't have a control. You can flip these, but I don't want to do that. Oh wait, you better be right-handed. It is right-handed. X cross Y Z. That's good. Okay, very good. So save it. Now we're going to.
Hey, Doctor.
Yes.
I think your axis is in the wrong plane. That's the plane that's aligned with your global.
Oh my God, you're right. Thank you. Yes. Okay, so let's do this. Let's fix it. Yeah, I thought something was different. I double click on this, and let me see if I unclear that. No selection. I'm going to select this point. Okay, that's better. And now X, I'm going to use this axis. Thank you for mentioning because we would have noticed it later, but anyway, that's better. Good. Okay, save everything. Okay, now we're going to go to generative shape design. And now we're going to extract the top and the side. Where is it? Extract. Let's find it. Remember, I reset my toolbar, so they all went into that hole. Now I've got to drag them out. There is the, extract is under boundary, I think, somewhere there. Same place that join is. Yeah, extract right there. Now, if you do it like this, you have to do it twice. But if you pre-select it, it's not a big deal. If you pre-select it, you can do it at once. I mean, the difference is fraction of a millisecond. Where is this? Whoa. Dismiss. Let me actually close that. Okay, so where are we? Extract. Where was this? Right there. We'll do it at the same time. Not a big deal. You better join it. If you don't join, then what's going to happen is that there's going to be node numbers here, there's going to be node numbers here. When you pressurize it, this will fly away. It'll say factorize matrix computation. It'll say join it, join it, join it. This and that. And we say, okay. And we're pretty much done. Save this. The rest of the problem is exactly like before. You go to generative structure analysis. That's, oh, material we forgot to do. By the way, you can do material later on, but let's not do that. You can do that material in the place that it complained.
Hey, Professor.
Yes?
Question. Why do you need a new axis when you can just use the global axis for the restraints?
I can't do it for the other side. I can do it. The other one is at 45 degrees. If this was 90 degrees, it would have been okay. But on purpose, I rotated this thing by 45 degrees so that this is not global anymore. Global does not have its x along that line. This one of the edges is okay, global, but not these two edges because they're at 45 slant at a slanted surface.
Oh, I see. I see. That makes sense.
Yeah. Okay, so what did I do? Apply material. I think did I apply metal, steel on the part? It's okay. Save it. And now we're going to go to generative structure analysis. I want some comments here. I want some comments. What's going on? What the heck is this?
I think it meshed your entire body instead of just the surface.
We don't need the surface. You have to mesh. It's not going to do it for you, but it will mesh the object, and we don't want it, so we're going to delete that. And you better delete the 3D property. Not there. 3D property, otherwise you say, I don't know what to do because I don't have an element going with me. Now you mesh the surface. CATIA will not do it for you. So I want to mesh this. Because I joined them, it'll do it both of these at the same time. This guy's bothering me, so I'm just hide it. Okay. And I don't know, I said 0.1, and then we made the parabolic, fine. Oh, geez. It's not good. It's too much. 0.2. Oh my God, this is also too much. I don't know, maybe 1. No, 0.5. Look, you make that thing small, you may have to sit there for a long time, and eventually you have to kill that job. Okay, I'm just letting you know. On the test, unless you're asked to, use default size and sag and linear elements. We'll talk about this thing later. Again. There we are. Okay, fine. This is a little bit finer than the other one, but that's okay, no problem. Deactivate. Let's proceed with the rest of the problem. Okay, pressure. Let's do the. Oh, how about the thickness? Let's put a thickness here. On the joint, it was 0.1. That's fine. Pressure. Where's the pressure? On this face and that face, both of them. And the direction looks okay. It's pressurizing it. Okay. Why don't we save our analysis before this thing power goes off, and then we lose everything that I did after the part save. So file, save management, analysis, save as. We had this one before, and we called this thing surface extraction, I think, something like that. Okay. All right, almost done. Okay, now the restraints. This time I'm going to be going against my own advice. Okay. Now be careful. First of all, remember in the last run I changed global to user. It stays like that. Okay. I suggest we put it back to global. When needed, we're going to go back. Put it back and use it. So this bottom in the global direction does not move in direction Z. Rotations opposite, just like before. Those back edges now, before it was front edges, now it's a back edges because of the comment that your classmate made. So user define this edge and that edge lies in the YZ plane. They don't go in the direction X. Okay, global. And these two front edges, these two, this guy and that guy, they, with respect to the user one, and the user coordinate system is the one that I just created, they lie in the XY, and once again, therefore, they don't go in the Z. Rotations is opposite. It's easy to make mistakes. Now, remember, I didn't put any identifiers here, and if I have to go back and check it, I don't know what they are. I have to look at the screen. You know, it's a bad idea. I try to save, 2 seconds, and then I regret it later. Okay, so let's run it. I hope I didn't make a mistake. If I had not joined those two, they would have gone their own way. It would not have finished. Believe me, this is okay. Yeah, right. Same thing. Now deflection, almost the same. You can see that. Almost the same. So let me stop the recording here, and then I'll entertain any questions that you have. It's exactly 15 minutes. I like it. And this, of course, is going to get posted just like the rest of them. Stop recording.